Hi there, it's Tim, Golf 5 Tango Mike, and thanks for stopping by. If this is your first time, think about clicking subscribe if you like what you see, and that notification bell for any future videos. And if you're a regular or if you've been here before, then welcome back and thanks for coming back. Now, I thought we'd look today at half-wave vertical antennas. Now, we've covered a few of these in the past, in some videos I covered recently anyway, where we've looked at end-fed half waves, we looked at the 20 meter and 10 meter dual band one. I'll put a link there for you. We've also looked at the 3-band version for 40, 20 and 10. Again, I'll put a link up there. And both of those antennas, wire antennas of course, fed at the bottom with a 49:1, and they go up a fiberglass pole. Simple. Now, half-wave verticals work really well, and in fact, before I go into this, I've had a message from somebody who made the antenna that I featured in another video, which I'll put a link up to there, which was the 20 meter coaxial end-fed vertical, effectively the T2LT if you want for 20 meters, vertical dipole basically. And it was Sylvia, that's right, TK4TH over in Corsica, and she made one of these antennas up and has had great success, and she's been working into ZL, into Japan, into the Caribbean. She's had a whale of a time with it, and I came across her on air about a week or two ago when I was working mobile down by the beach, which again you may have seen the video of that. It's the most recent one I think I've released, and she had a whale of a time, and she's having a lovely time with that antenna. So well done to you, Silva. I hope you're really enjoying it, and thanks for having a go at making the antenna. I'm really glad it's working well for you. Back to the matter in hand. Right, so half waves. Now I'm going to focus on 10 meter half waves, not 10 meter long, a half wave with a 10 meter band, which you can also extrapolate this for you guys who like using 11 meters CB, 27 megs, which I still like to dabble in as well. So if you remember, we made one of these antennas, or I made one of these antennas and I tested it and it worked really well. Link up there for you for the T2LT for the 10/11 meter band. So we're looking at that particular antenna, but you can use this for any half wave on any band actually, because it'll just be about how much of a fraction of a full wave, if you like, you're going to mount each antenna up above the ground. So we're going to look at 5 different scenarios. We're going to look at what the antenna performs like if you ground mount it as a vertical half wave. We're going to look at how the antenna performs if you mount it a quarter wave above ground. So in this case for 10 meters, about 2.5 meters above the ground. For half wave above the ground, we're going to look at that as well, which for 10 meters will be 5 meters off the ground. As a 3/4 wave off the ground, so we're looking at 7.5 meters off the ground. And finally, as a full wave off the ground, so we've got the antenna for 10 meters, 10 meter vertical would be now 10 meters or just about 30 odd feet above the ground. So we're going to look at each one of those 5 scenarios and just see what effect it has in terms of the gain. And I guess we're answering the question, is it worth the bother of putting these antennas up that high? Let's look then at the table I've put together using data from MMA&A, which compares the gain of a half-wave vertical depending on the different heights that it's mounted above the ground. Let's see. And by the way, as I said, we're looking at 10 meters here as our band of choice. You can use 10 or 11 meters for this. But of course, as I said, you can extrapolate this for any other band. All right, let's have a look at the table. So what we've got there, first of all, we've got the 5 different scenarios, ground mounted, all the way up to full wave above the ground level, okay? And on the top there, we've got the different takeoff angles. So we've got 5 degrees, 10 degrees, 15, 20, and 45. And we're looking at the gain, okay? The gain that we've got in terms of against each of those different takeoff angles, against each of the different heights above the ground. So let's have a look at the first situation here. So we can see I've highlighted in yellow, we're looking at 5 degrees off the horizon, what the gain would be. So for ground mounted, you're looking at minus 5 dB. Now that is just about a little bit better than a ground mounted quarter wave vertical, which should be about minus 5.8, minus 6, depending on what you look at. So it's slightly better. Then if we sort of heighten that antenna up a bit by a quarter wave above ground level, we're then looking at minus 2.3 dB. So we've got a nice little increase of nearly 3 dB. So we're effectively doubling our power by doing that. Then if we put it up halfway above ground level, Suddenly, the base of that antenna is our half wave above the ground, and we're looking at a gain now of minus 1.1. So again, we've added another dB and a bit onto it. If we then put it 3/4 of a wave above the ground level, we're now on 0.5. So we're nearly 6 dB better than a ground-mounted half wave. And if we go to the full wave above the ground, which for the 10-metre band, don't forget, is about 33 feet above the ground, 10 metres above the ground. And of course, we try to do that with 20 metres, and you're looking at being very high, about 66 feet above the ground. Then you're looking at a gain of 1.6. So from being ground-mounted up to being a full wave above the ground, we're looking at about 6.5 dB, just over an S point. All right? That's the difference between what we're looking at here. Now, going back to the table, if we then look at the 10, 15, 20 and 45 degrees going across there, we see a similar pattern. So for 10 degrees, we see an increase in gain as we go higher above the ground. There are some anomalies though, which I put in blue. So at 15 degrees, for example, half wave above the ground, we can see it's actually slightly worse than being a quarter wave above the ground. And we'll look at that in a minute, okay? Certainly for 20 degrees, it's slightly worse as well as a half wave again, but again, nothing to write home about. And at 45 degrees, I've looked at 45 degrees because that typically is around the range that we see some decent gain if we're looking at hitting sporadic E contacts. So on 10 meters, for example, if we're looking to get into Italy or Spain throughout the summer months, that kind of thing, that's the sort of takeoff angle that tends to help us a little bit. And if we go back to the table, we can see actually that when you put it up 3/4 or a full wave above the ground, we see a reduction in gain. So that's quite interesting, isn't it? We have that particular little breakup of the pattern there. And in fact, if we look at this, we can see, look, the angles of maximum gain. And if we look, for example, at the in yellow, we've got GA, that's the gain. And we've got the other one in ELEV, which is the elevation, the angle of elevation. So the peak gain, for example, for the top one, which is the ground-mounted one, is about 0.3 of a dB at nearly 20 degrees off the horizon. Then we've got tend to have an increase in gain at lower angles, except, of course, once we get to a half wave above ground, then the peak gain there is actually at about 38 degrees. So what we're seeing here is a bit of a difference in the pattern, if you like, between these different heights, which is quite interesting, isn't it? Well, if we look at the full wave, if you get your 10-meter antenna, your Antron 99 or something, at height level, for example, then effectively, if we look at the table here, we're going to look at a gain then of 3.2 dB at 9 degrees off the horizon. That's looking really, really nice. That's looking really nice indeed. So height kind of is might. You know, it does help a little bit. And if we look at the pattern itself, look here, in yellow on the left-hand side, that goes up from about 0 to about 20 degrees off the horizon. That's tend to be where we're looking at DX country when we're coming to an antenna. That's mean that low angle of takeoff for that single hop. And those different colours represent the different different heights above ground. So, for example, the purple one there, nearest the yellow, is the one where we've got it a full wavelength above ground. And it tends to follow the pattern that where we have it higher up above the ground, we have greater gain at lower angles of takeoff. Looking back at this again, though, if you see on the left-hand side, there's a little blob, nearly halfway up on the left-hand side. I've drawn a little grey or black blob on there. Now that is about 45 degrees, and you can see there that actually those, the outer one, which was the one that was mounted a full wave above the ground, is actually not doing very well at about 45 degrees, as is the yellow one, which is the one which is 3/4 of a wavelength above the ground. So, you know, it's horses for courses, isn't it? If you're going for true DX, it's basically the case that height is might when it comes to a half wavelength vertical. Last thing to bear in mind is, what does this mean for you in terms of operating portable? Because we mentioned about putting them on the roof, but clearly you can't take your house with you when you go up on a hill, or if you go down by the sea, or go wherever you go to operate portable. Again, we're looking at 10, 11 meters here as our bands of choice. If we look at the table here, look, we can see that when you're taking a pole with you to mount a vertical antenna, usually, of course, a fiberglass pole, when you're obviously ground mounted is ground mounted, but when we're looking here at quarter wave above the ground, we're effectively using an 8-meter pole, aren't we? And we're putting the antenna probably about 2.5 meters up that pole, so at the tip of the wires at the very top of the pole. So if you use an 8-meter pole to put your T2LT up, for example, your wire for maybe 10 meters, then if you're chasing DX, you're going to have an improvement of nearly 3 dB than if you ground mounted it. If you took with you a 10-meter pole, so if you're operating maybe from your car and you can carry a 10-meter pole up with you, then we got an increase again of about 1.2 dB. So we're now nearly 4 dB better off than if we ground mounted it. If you then take up a nice chunky spider beam pole, a 12-meter job, and therefore you then put in the base of the antenna about 7 meters above the ground, which is near enough to 3/4 waves above the ground level. Looking back at this again, we can see that at 5 degrees, we've now got a gain of 0.5 dB. So we're now basically as good as an S point stronger than we would be if we ground mounted it. And even compared to the 8-meter pole, for example, we're nearly 3 dB better off, which is effectively doubling your power, all right? So you might be 500 meters above sea level on a hill. Even if, though, you decided to take a bigger pole, it's still going to make and get your antenna off the ground a little bit more. It's still going to help, all right? So height is might in terms of the hill you're on, but height is also might in terms of how high you get your antenna off the ground, okay? So don't rely on the hill to do all your work for you. If you're looking to DX somewhere, to join a net, or if you're looking to maybe try and make some DX contacts if 10 or 11 is open, okay? Get the antenna off the ground as much as you can. Higher the better. As you can see, if you use that spider beam pole, you're going to be about 3 dB, get my words out, 3 dB better off than you would if you're using, say, an 8-meter pole. If you want to see a bit more information about how to make some of these antennas we've mentioned today, I'll leave a link for one of them here, which will be the 10/11-meter version of the T2LT. Thanks for watching, 7.3, and take care now. Bye-bye.